Hello everyone, I'm 𝗟𝗶𝗿𝗲𝗄 Somantri.
My name is Lintang Putri.
I'm Bagus.
My name is Ferdinan.
I'm Zidan from Group 2.
So here we will present our machine learning project on house price prediction using linear regression. So which is in this presentation we will explain about the project 1. So our goal is to analyze key features affecting house prices and develop an accurate prediction model using the California housing prices dataset from Kaggle and insight from Langkah, Mudah, Belajar machine learning dengan Python untuk pemula by Randi Adrika Putra. So we here apply supervised learning with linear regression. This method effectively identifies relationship between houses, feature and prices, and making our model available for buyers, developers, and policymakers in real estate decision making.
In step 1, load library and why do we use them? Now let's move on to the technical aspect of our project. We will explain the step-by-step process of implementing linear regression for house price prediction. In step 1, we start by loading the necessary libraries for data processing and modeling building. We use libraries like Pandas and NumPy for data manipulation and numerical operation, while Matplotlib and Seaborn help us with data visualization. For feature scaling, we rely on standard scalar to split the dataset into training and testing set. We use train, test, split. Finally, linear regression is used to build our model, and mean square error and 𝗟𝗏𝗿𝗀𝗃 help evaluate its performance. In step 2, load data and initial exploration. In step 2, we load the California housing price dataset from Kaggle using Pandas read CSV and perform an initial exploration of the data. We check for the number of entries, data type, and any missing value with head and info. We find that the dataset contains 20,640 rows and 10 columns. K columns include longitude and latitude, total rooms, total bedroom, and median income, and also median house value, which is our target variable. We also identify missing value in the total bedroom column that need to be addressed. Step 3. Data cleaning. Before building our model, we ensure data accuracy by handling missing value and optimizing feature. We fill 207 missing entries in the total bedroom columns with the median to maintain consistency. Next, we convert the categorical Gaussian proximity column into numerical format using one-hot encoding. To simplify the model, we remove less relevant feature and validate the dataset for any remaining inconsistency. Finally, we save the clean dataset as cleaned California housing CSV to streamline feature processing.
Step 4, it is data manipulation. Now that our data is clean in step 4, we focus on preparing the data for modeling by ensuring it is informative, error-free, and ready for processing. With a clean dataset, we enhance it by adding 3 key features: room per household, bedroom per room, and population per household to capture housing patterns. We handle errors by replacing infinity values with NaN and filling missing values with 0. To improve model efficiency, we normalize all features using standard scalar. Finally, we split the data into 80% training and 20% testing. It is 16,512 versus 4,128 records to ensure reliable model evaluation. Moving into step 5, it is exploratory data analysis, or we call it ADA. In step 5, to get insights before modeling, we program ADA to better understand the patterns in our data, find relationship between variables, and identify any anomalies. Using the scribe bracket, we found house prices from $14,999 to $500,001, averaging $206,856 with a notable price cap at $500K. A correlation head map show median income. It is 0.69 as the strongest predictor, while total rooms and households, it is 0.92, suggested potential multi-collinearity.
So after preparing the dataset, we move the core of our project. There is implementing machine learning using linear regression. So here in step 6, we implemented linear regression to predict house prices using selected feature like housing median age and population per household, while median house value serve as the target variable. The dataset was split into the 18% training and 20% for testing to ensure generalization and prevent overfitting. So the model learned the linear relationship between feature and house prices with performance evaluated using mean square error or MSE and R square score. The MSE was 6.8 billion and the R square score 0.4811, indicating the model explained 48.11% of price variation, and key predictor included median income most influential, and while population and total room share up a weaker impact. So income remained the strongest determinant of house prices, highlighting areas for model improvement.
Step 7 about the visualization. To further analyze our model accuracy, in step 7 we visualize key insight to better understand how the model performs and identify areas for improvement. The scatter plot of actual versus predicted values show good accuracy for homes priced $100 until $300 but underestimate higher price house. The residual plot indicate random error for lower price but heterogeneity for higher ones, suggesting a log transformation or non-linear model could improve performance. And future important analysis confirmed that median income is the strongest predictor, followed by household and population density, while total rooms had a minimal impact. The error distribution plot show most error near zero, but extreme outliers suggest lasso or ridge regression could help. Lastly, the geographical scatter plot reinforced the coastal cities like San Francisco and LA have the highest price, highlighting the importance of location in refining our models.
Now that we have analyzed the model, let's summarize our insight, final predictions, and also the conclusion. The insight is that from our perspective about business and property investment highlights that median income is the primary driver of house prices, with a $1,000 increase leading to a $4,200 rise. With my perspective about social and economic aspects of society emphasize that population density affects affordability, with the wealthier areas having higher prices due to a limited land supply. And Lintang's perspective about urban planning and macroeconomics notes that infrastructure such as public transport and business hubs boost property values, with property near transport routes growing over 15 and 20% faster. And Zidan's perspective about technology and data science in real estate show that machine learning improves house price predictions with 85 to 90% accuracy. Lastly, Bagus' perspective on business strategy and market analysis advises the investor to target rising income areas and consider open space home designs for differentiation, with the final prediction over the next 5 years, property in high income business districts and coastal areas will grow to 20 to 30% faster due to strong demand, while densely populated area with poor infrastructure may stagnate or decline. And finally, the conclusion: higher median incomes drive property values. Infrastructure is the key for growth, and data science enhances market predictions, benefiting investors. Inclusive housing policies and other urban planning are essential to prevent social inequality in housing assets.